If we are going to do anything useful in chemistry in a quantitative sense, we're going to need to understand about chemical equations, and most importantly, we're going to need to understand how to balance chemical equations. So in this video, we're going to start by reminding ourselves what chemical equations are, and then we'll finish off with some hints and tips about balancing chemical equations. A chemical equation is a shorthand notation for representing a chemical reaction, and you can see an example of a chemical equation here representing the combustion of methane, CH4, in the presence of oxygen to produce carbon dioxide and water. And this is a reaction you might be familiar with because methane is the chief component of natural gas, and this is the reaction that takes place on gas stoves and in gas ovens. Chemical equations contain chemical formulas of substances, either elements or compounds. CH4 is the chemical formula for the molecular compound methane. We've also got the formula for elemental oxygen, O2, a molecular element. And over on the right-hand side, we have the chemical formulas for the molecular compounds carbon dioxide, CO2, and water, H2O. Each of the substances in this chemical equation are given a subscript to represent the state of matter that they exist in at room temperature and pressure. So gases have the subscript G, liquids have the subscript L, and solids have the subscript S. The plus sign on the left-hand side of the chemical equation means reacts with, and the arrow means transforms to or produces. In this particular case, the arrow has a Greek capital delta on top of it, and that indicates that this particular reaction actually requires a little bit of heat to kickstart it. The substances on the left-hand side of the arrow are called the reactants, and the substances on the right-hand side are called the products. The big numbers in front of some of these substances are called stoichiometric coefficients, and they are there to balance the equation. In the case of the O2 molecule, the stoichiometric coefficient implies 2 lots of the oxygen molecule. And since each oxygen molecule has 2 atoms, there are 4 oxygen atoms in total on the left-hand side. Over on the right-hand side, the 2 in front of the H2O means 2 lots of the water molecule. So we have 2 times the 2 hydrogen atoms, giving 4 hydrogen atoms in total, and 2 times the 1 oxygen atom, which is 2 oxygen atoms in total for the water. We also have a couple of invisible stoichiometric coefficients. The number 1 is never written explicitly in chemistry, and in a balanced equation, if a particular substance in the equation does not have an explicit stoichiometric coefficient, then a stoichiometric coefficient of 1 is implied. So we can represent a chemical reaction using a chemical equation such as this, where each of the substances are written as a chemical formula. Or we can represent them using structural formulas. The use of structural formulas is good for being able to identify the number of molecules involved and for tracking exactly where each atom is on both sides of the equation. Remember, a chemical equation is simply a rearrangement of atoms. So in this particular representation, we can see we've got 1 molecule of methane reacting with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. By using structural formulas, we can easily track how the atoms are being rearranged. For example, on the left-hand side, we can see we've got 1 carbon atom that is tied up in the methane molecule. And on the right-hand side, we've also got 1 carbon atom that is tied up in the carbon dioxide molecule. On the left-hand side, the 4 hydrogen atoms are tied up in the methane molecule, whereas on the right-hand side, we've got 4 hydrogen atoms tied up in the 2 water molecules. The 4 oxygen atoms on the left-hand side are tied up in the 2 oxygen molecules, and we've got 4 oxygen atoms on the right-hand side spread across the carbon dioxide molecule and the 2 water molecules. So this equation is said to be balanced. We've got equal numbers of atoms on both sides of the chemical equation. A chemical equation such as this is a quantitative statement of the relative amounts of substances present in the reaction. And what that actually means in this case is that exactly 1 molecule of methane will react with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. So if a chemical equation is a quantitative statement of relative amounts, we actually know that the SI unit for amount is the mole. And so a different way of interpreting this chemical equation would be to say that 1 mole of methane reacts with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. And this mole interpretation of a chemical equation allows us to do some pretty useful things, like calculating the amount of products from a given amount of reactants, or calculating the amount of reactants required for a given amount of another reactant. And we will see how important this mole interpretation of chemical equations becomes in later videos. If we now turn our attention to balancing chemical equations, then, in general, if we know both the reactants of a chemical reaction and the products of a chemical reaction, we can write an unbalanced chemical equation. And we can simply balance that equation by using the stoichiometric coefficients, those big numbers that are placed in front of the chemical formulas in a chemical equation. A word of warning here, however, we should never change the subscripts in a chemical formula to try to balance an equation. By doing that, we actually change the chemical formula and therefore the identity of those compounds or elements. So the only way we can balance a chemical equation, once we've got the correct chemical formulas written in place, is to change the stoichiometric coefficients, those big numbers at the front of each substance. So we'll use the combustion of hydrocarbons as an example of how best to balance chemical equations. A hydrocarbon is any compound that contains just carbon and hydrogen. And the X and the Y here indicate that there is any number of ratio of carbon atoms to hydrogen atoms representing hundreds, if not thousands, of hydrocarbons that exist. Now, all hydrocarbons will combust in the presence of oxygen to produce carbon dioxide and water. So this equation here represents the general chemical equation for the combustion of a hydrocarbon, and importantly, we are able to identify all other reactants and products in the chemical equation. So if we choose a particular hydrocarbon, say propane, C3H8, we can now write down an unbalanced equation for the combustion of propane. Propane, C3H8, reacts with oxygen to produce carbon dioxide and water. And at the moment, this equation is unbalanced, and we need to balance the equation by finding the appropriate stoichiometric coefficients to place at the front of each of these substances. It's unbalanced because we have 3 carbon atoms on the left-hand side here and only 1 carbon atom on the right-hand side. We have 8 hydrogen atoms on the left-hand side here and only 2 hydrogen atoms on the right-hand side. And at the moment, we have 2 oxygen atoms on the left-hand side and a total of 3 oxygen atoms on the right-hand side. So in order to balance this equation, it is best to take a bit of a systematic approach, and here are some hints for doing this. The first thing you should do is identify any elements in the equation, and we should leave them to last in terms of getting equal numbers of atoms on both sides. So for example, oxygen here is an element, a substance that contains only one type of atom. So we're going to leave the oxygen atoms till last when we are balancing this equation. It is also useful to identify atoms that appear more than once on each side of the equation, and we're going to leave them until later to balance. And what I mean by this, for example, is that oxygen appears in more than one substance on the right-hand side. So that's another reason to leave the balancing of oxygen atoms until last in this equation. We should also identify any hydrogen and oxygen atoms and leave them till later as well, particularly if water is in the chemical equation, because it is easy to balance hydrogen and oxygen atoms by adding or subtracting water molecules in the balancing process. And then finally, we're going to balance all remaining elements first. So in this particular case, that means we're going to be balancing carbon first. We've got 3 carbons on the left-hand side and only 1 carbon on the right-hand side. So in order to balance the carbons, I'm going to put a big 3 in front of the carbon dioxide, which gives me 3 times 1 carbon atoms on the right-hand side, and that's good because it matches the 1 times 3 carbon atoms that we've got on the left-hand side. So now 3 carbon atoms on each side. The next element I'm going to balance is hydrogen. Remember, we're leaving oxygen till last. I've got 8 hydrogen atoms on the left-hand side and I've got 2 hydrogen atoms on the right-hand side. So to balance the hydrogen atoms, I will place a big 4 in front of the water, which gives me 4 times 2 or 8 hydrogen atoms on the right-hand side, which balances the 1 times 8 hydrogen atoms on the left-hand side. So what that has done now is given me a total of 10 oxygen atoms on the right-hand side of this equation. The 10 oxygen atoms come from 3 times 2 oxygen atoms in the carbon dioxide, which is a total of 6, plus the 4 times 1 in these 4 water molecules, leaving me a total of 10 oxygen atoms in total on the right-hand side. To get 10 oxygen atoms on the left-hand side, I'm going to put a big 5 in front of the O2. And that gives me my 5 times 2 equals 10 oxygen atoms on the left-hand side to balance out the 10 oxygen atoms on the right-hand side. This equation is now balanced, and we've used a systematic approach to do it. And it's always a good idea to do a final check to make sure we haven't made an error. So we've got 3 carbons on the left-hand side and 3 carbons on the right-hand side. We've got 8 hydrogen atoms on the left-hand side and 8 hydrogen atoms on the right-hand side. And finally, we've got 10 oxygen atoms on the left-hand side and a total of 6 plus 4, which is 10 oxygen atoms on the right-hand side. In the next couple of videos, we're going to look at more complex chemical equations to balance, including more examples containing molecules, and we'll look at what to do with balancing chemical equations involving ions and polyatomic ions.